We're starting with the amide. We're using an excess of water, the same type of equilibrium process, to produce the carboxylic acid. The key difference in this balanced equation is the ammonium ion. So I've used a stoichiometric amount of acid to end up not with an amine, but an ammonium ion in the hydrolysis process. Water, a weak nucleophile, neutral, not charged. Need to activate the electrophile, that's the amide, so we need to protonate it. That you've seen before. It's a different chemical example of the same thing. Activate the electrophile. Hydrolysis, so it's water that's the nucleophile. New carbon-oxygen bond. Rearrange the position of protonation. This is a heteroatom of a lone pair to break the carbon-nitrogen bond this time. And then a loss of a proton to complete the mechanism to get you through to the carboxylic acid. So the amide has become a carboxylic acid and an amine at that stage in the mechanism. However, the key difference between this and the examples that you saw in the ester series corresponds to the key difference between esters and amides, the nitrogen atom that's present in the amide. So the key difference here is this very last stage, that in the presence of the acid conditions used for this, the amine that's produced will be protonated. And if the acid conditions are strong enough, that protonation reaction will dominate. And so you'll end up with what I showed you at the outset, the carboxylic acid in its associated form in the acid conditions, and the protonated form of the amine, the ammonium ion. Consequence of that is the following. This ammonium ion, 4 bonds to a cationic nitrogen, that structure has no lone pairs. If it has no lone pairs, then the nitrogen atom of the ammonium ion cannot be a nucleophilic center. And the reverse reaction, which otherwise would occur, would involve the neutral amine with its lone pair acting as a weak nucleophile. But it can't if the acid concentrations are high, because there is almost none of that species present at equilibrium. The more basic amine is almost entirely protonated. It's taken out of the mechanism by its protonation step, generating the ammonium ion, which can't act as a nucleophile. So the reverse reaction is blocked out under those acid conditions.